Lesson 37, Neural Networks 2, class number 2. Now we're going to start actually getting into neural networks instead of our perceptron network. I just want to go over why we want to do that. So let me give you a couple of pieces of data. We'll let greens equal 1, and we'll let red equal 0. Suppose we're trying to classify two different things, and maybe we have some data that looks, if you have an x1 and y1, here, let me put that on here, x1 and x2, I should say, x1 and x2, then maybe your data might look something like this, where a line will not go through and separate this data. So now what we need is something that looks like a curve. So a non-linear, even though a line is a curve, so now we're talking about a non-linear curve. So there are three things that we need to do in order to ensure that our new version of this type of model is able to fit things like this, or data that looks like this. So we got to introduce a new nonlinear activation function. And I went through two of them, or two more than we're going to talk about today in our notebook last night. But today we're just going to talk about the sigmoid function. The second thing we need to do is introduce hidden layers. And the last thing that we need to do, or the third thing that we're going to do today anyway, is we're going to talk about the need. So we need multiple nodes in our layers other than the input layer. So we've seen already that where we have multiple input nodes in a layer, or multiple nodes in an input layer. Today what we need to talk about are if I have multiple output or hidden or whatever. So that's going to be the idea. That's what's going to take us going from dealing with vectors and dealing with matrices. So let's go ahead and get started with so we've already talked about the Heaviside function, and I will reintroduce that one and show you what that looks like. Again, it's in the R notebook. I put them right beside each other in the same graph in the art notebook, so you can go there and check that out. The one that we're going to talk about, I put it in sort of this red color here, this salmon color. But the one that we're going to talk about is the sigmoid function. So let's look at the Heaviside first. And just realize what it's doing. So it's converting any real number into a 0 or a 1, into a 0 or 1. And if you look at it in terms of like neural nets and perceptron stuff, this is not firing. And I'll put that in with the quotation marks, or off, if you will. And this is firing. So the neuron or the perceptron is firing versus not firing, or it's on or it's off. So this might be considered on. What does it look like? Well, let's draw the picture of what it looks like, and then we'll actually or show you what the function is. So that's what it looks like. And the function is f of, this is that step function that we talked about yesterday, but it's a little bit easier when you're not summing a bunch of things. So it's 0 when x is less than 0, and when it's greater than 0, we're going to let it be 1. So that's the Heaviside function. So the sigmoid function, what is it doing? What makes it, I guess, a little bit better, if you will, is now we're converting real numbers into numbers between. So numbers between 0 and 1. And what that allows you to do is say, so firing isn't necessarily just a 1 or a 0, or if the sum is greater than, or in other words, the hard things that are considered with the Heaviside function. Now you can have maybe multiple outputs, and one can be 0.1 and one can be 0.05, and maybe 0.1 is firing because it's bigger than 0.05. So that's the idea that we can now use with the sigmoid function is talk about relative neuron firing. And so that's the idea behind that one. And so what does that one look like? Again, it's in the It's in our notebook, but it's asymptotic to 0. And then when it gets close to the y-axis, it starts coming up a little bit, intercepts about 0.05, and then again it's asymptotic to 1. So if this were 1, it's not done very well, but it doesn't go past 1. It converts all numbers into real ones between 0 and 1. And so what does that function look like? It's sometimes, and that's why I put it on here, sometimes you'll see it called the logistic function. I tell you what, I'm going to also, let's use this. Let's call this one HS for heavy side, and let's call this one sig for the sigmoid. I don't need this anymore. It's just 1 over 1 plus e to the negative x for x for any number. All right, so that's the sigmoid function. That's what it looks like, and that's sort of what it's trying to do. Now what we can do is come down here to what we need to do now is talk about the derivative. And the reason why I need the derivative is when we start talking about the error and what to do with the error and how to adjust weights. But we find out that the sigmoid function, if we do a couple simplifications, that it ends up giving us a pretty simple derivative to deal with. So let's write the sigmoid function again, and then let's take its derivative. And I'm just going to use the quotient rule. So low d high minus, so low 1 plus e to the negative x, d high, which is 0, minus high, d low, so that's a negative 1 e to the negative x over low squared, 1 plus e to the negative x squared. And let's rewrite that. Let's do some simplifications. We know that goes to 0. This minus and negative terms plus a positive, and we're just left with e to the negative x. And I'm going to go ahead and break this thing up into two terms, if you will. One term having a 1 plus e to the negative x, and then put a 1 over. And hopefully you see why. Because if you notice, this is just our original function. So I'm taking the derivative and I get the original function in the derivative, which is pretty neat. But it doesn't stop there. The neatness doesn't stop there. So let's keep going. We'll have another line here. I'm going to remember my sig x, so it's coming. And then I'm going to multiply, and then I'm going to do this little math trick that you've probably seen before, where I add 0. What do I mean by adding 0? Well, I put a 1 on the left-hand side, and I subtract 1 on the right-hand side, and we just leave the denominator the way it is. And we basically just added 0 to the numerator, so we haven't really done anything, so it's the same, it's equivalent. And now I'm going to break this up. So I got sig x. So sig x is multiplied by 1 plus e to the negative x over 1 plus e to the negative x, and then minus 1 over 1 plus e to the negative x. Okay, so let's talk about this just for a second. So you might be used to seeing it done this way. So starting from here and then simplified by, combining the terms with denominators, right? So these denominators are the same. So that's all I mean. All I need to do is take this and subtract that and put it on the numerator. So, but we've just done it the opposite way. So that's the only reason I want to point that out. We've taken this and we've broken it up into this. And the reason why we did it is, again, the same, was so that we can notice, obviously this piece is pretty straightforward. This is obviously equal to 1, so that's a good thing. And then this piece, again, is equal to our original function, sig x. So what we're saying and what we're going to need in our next class is the derivative of sig x is simply equal to sig x times 1 minus sig x. So I'm going to put a little bracket around there. I even put a star on it just so we don't forget it. I know we may or may not forget it, but I'll rewrite this again tomorrow just so we remember our next class. So the next thing that we want to talk about is this idea of forward propagation. And what forward propagation lets us do? I know we've seen a perceptron network already, and we sort of know what's going on with the perceptron network. But what we want to do now is explain or try to talk about it, given some input, how do we go through the system in order to get the output? So that's our intent for this piece. So before I get started, let's go ahead and label. So this is my input layer. So these are layers of your network. This is my hidden layer. And this is my output layer. And another thing that we need to remember is the bias node. So the 0 node it's called the bias node, and it always inputs a 1. So I don't need to do anything. I don't need to know what's going on. I know a 1 is always going into my bias node, and I don't need a bias node for the output layer. So if you remember from last class, we need that bias node to help us out with this. And the next thing that we want to do is, yeah, I kind of messed that up. Hold on. I'm not going to call this output. We're going to call this the final layer. And just understand that it's called output in some books. Today, or the rest of this class, if you will, we're going to call it final, and final is the output layer. Okay. So let's remember what a perceptron network has on it. So it has these W's, and that was the model. So we have W0, and then, so that's coming from input layer node 0, and it's going to, here, let me just sort of trace this out. So I'm going from node 0 to node 1. So this is the weight 0, 1. The next one is the weight W02. So you can see W02. And then we just keep that same sort of idea. I got W11, W12, 21, and so on and so forth. I'm going to label all these. I probably won't do the next one, but you see what's happening here, right? So that's 3-1 and 3-2. Now, the weights that are located in here, if you start looking at the indices, right? So I got a 1-1, a 1-2, 2-1, 2-2, 3-1, 3-2. That sort of looks like a matrix. So if you think about it like that, well, I can just call this W, capital W, and I'm going from my input layer to my hidden layer. So I'm going to call it WIH. So it's the matrix WIH, all capital letters. And it has how many rows and how many columns? Let's think about that for a second. So it has the number of rows in my input, right? So 1-1, 2-1, 3-1. So I have the number of input. Here, let me move this down a little bit. It's sort of getting in my way. And now we can make this a little bigger. So I have WIH will be W11, and then how many columns do I have? The number of columns equals the number of nodes minus my bias in my hidden layer, right? So I'm not including my bias in this matrix. So it's W11, W12. Okay. So if you don't include your bias node, then we can write the matrix as a 3 by 2, meaning that's the number. So if you come up here and you look, we're doing a 3 by 2 by 4 network, and this is an example of one, and it's just sort of arbitrary, the numbers that I chose there. But I have a 3 by 2 matrix that takes me from my input layer to my hidden layer. And if we do the same sort of, we haven't talked about the bias. So the next piece is I call it the I bias vector. And I'm just going to put a big vector sign over it. And all it does is it has the same number of components that I have in my hidden layer. Again, minus the bias. So I got W01 and W02. So these two, this matrix and this vector, these two data structures, if you will, if you're going to talk about them as an R thing here in a few minutes, they capture all of the weights that are in my network, or at least from the input layer to the hidden layer. Now what we'll do is we'll talk about W01. So let's start. So all of these are a little different. I mean, these W's are all different. So these W's that are lined up over here are not the same as the W's that are from the hidden to the final. They're going to be different numbers themselves. And the way that we're going to capture those is the same way that the nomenclature-wise or notation-wise. I'm going to call this WHF, and it's going to have the same number of rows. So I don't need that many of them. It's going to have the same number of rows that I have hidden nodes, and I'm going to have the number of columns that I have as final nodes. So I'm going to have 2, so this will be a 2 by 4, and I'm going to put this underneath here, and this will be a 2 by 1. So this will be a 2 by 4 where I have W11 through W14, and obviously a second row. Okay, so that is my matrix that captures all of the W's that are assigned. They come from here and go to these nodes. And then we'll call this thing the H bias. And it is just a vector that has the same number of components that are in my final layer. And you can go back up here and check it out, right? So it has 4 of them coming out. Let's see, what else do we need? I think that's what we need as far as understanding what things that I need to capture. So what we're going to end up doing here is we're going to input in our input vector. So at some point we're going to have an x1 actually. Let's call that xi1. This is the notation that we're going to use in xi3. So this is my input vector, and it is x of I. It has 3 components. There's 3 things coming into it. And then what we're going to do is the same thing that we did with the perceptron network. We're going to take x11 and we're going to multiply that by W11, and that's going to be the part that comes into something in here. And before, when we were doing the perceptron network, we added all these up. So we added the xi1, W11 plus xi2 times W22 plus xi3 times W31, and all of and the W01 times 1, right? So we added all those things up, and then we use the Heaviside function to say what the output was. In this case, we're going to do the sigmoid function, but it's going to be the same thing where we multiply and then add up all those things together. So and then the sigmoid function comes through, and so on and so forth. So that's in general what we're going to do. All right, so let's get our notation for the input layer. That is going to be the vector xi, and that's going to be a vector that is, in this particular case, is going to be 3 by 1. So I'm going to keep track of all of the dimensions of each one of these pieces. And then what do we do to go from the input vector to the output vector? What do I mean by that? So the inputs are coming in, xi1, and I'm claiming that there's something coming out of this node, and we're going to call that OI1. This one's going to be OI2, and OI3. So how do I get from XI, so OI3 by 1? 3 by 1. This is going to be the first thing that we're going to do. So I'm going to have a big giant 1 over here. And all we're doing when we go from XI to OI is simply just set it equal to. So there really is nothing that's going on in and this is an actual I. It's not a subscript or anything. It's just XI. And that's going to be equal to OI. So nothing goes on in the input nodes. It's unlike the hidden nodes and the final nodes. We're going to actually do something inside those, but in this particular one, we're just setting them equal to. So the first thing that we do is we notice that these input vectors, I'm going to use an X for each one of them, and in the output vectors of each node, I'm just going to use an O. And now I need to go from OI to the input of the hidden layer. So what do I mean by that? Well, let me use another color. Let me use blue. So blue is going to come into here. And what it is, it's a combination of all of these things. And that's what's actually going to go into one. There's going to be a single number that goes into the node 1, the one node of the hidden layer. And we're going to call that XH for our X hidden. Actually, this will be X1. This will be the number that actually goes in there. The combination of all of these things that are sort of multiplied and added up is going to be XH2. So obviously we only have 2 components of this vector, so it's XH, and it's not a subscript. I keep trying to make that sucker a subscript, but it's not. It's XH, and then this is a 2 by 1. And remember, I mean, we sort of went through it just a second ago, but I'm going to go ahead and start writing it out. So we'll write it out up here. Going from so X, H, XH. Matter of fact, let's do it like this. Let's call it XH1 and XH2. So I'm going to do this one time just so you see the math, and hopefully you recognize that it's something that we can make a little bit easier. So XH1, the number that's coming in to this node, starts off with WO1 times 1. So that's what we'll start off. So it's just WO1 plus, come back over here, so it's W11 times X1, XI1. So W11 XI1 plus W22, not 22, it's 21, right? So you come back, so I'm coming into this node, I trace it back, it's W21 times XI2, W21 times XI2 plus, again, come back to the node, scoot it over, W31 times XI3. So W31 XI. And it's not a subscript. I keep trying to make it a subscript, but it's just XI. It's the component of the XI vector, which is the input vector. And so we get that, and then the XH2 is so that takes care of the arrows that are coming into from this side on node 1. So what I'm telling you is this XH1 is a combination of all of these arrows that are coming in. And the way that you do the arrow is you just take the weight on that arc and multiply it by actually the OI. Oh, I should have done the OI. Matter of fact, let's go ahead and get rid of all these. And so while we do this, so this would be OI1, OI2, OI3. I mean, they're the same in this step, but they're not going to be the same when we get to the next step. So that's why I want to make sure we clarify, or make sure we do it correctly. So WO2 plus W21 OI2, OI1. Let me make sure that's correct. So I'm now here. I go up, that's WO2. This one is W12. 12 times OI1. The next one is W22. So plus W22 OI2 plus W32 OI3. And again, just trace this thing back and make sure that makes sense, and it does. So what we notice, if we're matrix algebra people, is we can make our calculations much easier if we look at it like this. So these two calculations, if you will, can be summarized just by this being the I bias vector. So that's what this WO1, and we'll let this be XH vector, is equal to I bias plus, well, how would we get this two numbers here? The thing that W11 times OI1, W21 times OI2. Well, let's take this matrix out and just do the matrix multiplication. So W11, W21, W31, 1, 2. So what we're doing is taking all the W's out, and we're multiplying it by the vector OI1, OI. I'm going to need more space. OI1, OI2, OI3. Because this row times this column gives you this first one, and this row times this column gives you the second one. And our computers are really good at doing matrix multiplication, so it does it very quickly. So that's what we want. That's how we want to do it. Then we want to have this as, well, how is this related to WIH? Because that's not the matrix WIH, but if you come back over here and look at it, it's just the column has become the row, and this column has become the second row. So that's called the transpose. So it's the transpose of the matrix, and this is OI vector. All right, so with all that being said, if I want XH, all I'm going to do is take the previous thing that I found, which was OI. I'm going to have this matrix multiplication. So WIH, OI. So let's keep track of all of the components. And so this is a 3 by 1. This is a 3 by 1, just to make sure they line up. This is a 3 by 1. WIH transpose becomes instead of a 3 by 2, it's a 2 by 3. So these components line up, and it leaves you with a 2 by 1, which is exactly what we want for the number of the nodes going into the hidden layer, or the number of nodes that are in the hidden layer. Okay, so now what do we want to do with that vector in order to get the values that are coming out of that node? So I'm going to call this the output of the hidden layer 1. This one is the output of the hidden layer 2. And so I'll put this down here, OI vector, and it looks like it has 2 by 1. So it's a two rows for this particular thing because it has 2 nodes in it. So the calculation there is pretty simple. I guess it's a little more difficult than number 1 where you just set them equal to, but it's not that difficult. So all you're doing to get I called this thing H or I, when really it should have been H. So OH, it's the output of the hidden layer. And let's do the same thing here. So OH is equal to the sigmoid, the activation function. So we're not doing the Heaviside function now, we're doing the sigmoid. and you just take the sigmoid of the XH. And this will be a 2 by 1 because this was a 2 by 1. So all you're doing is going to each component and taking the sigmoid function of it. Okay, so that would be what we do to get from, so this is step number 3. This one is step number 2. The arrow that's taking you from xi to oi is 1, oi to xi is 2, and I sort of labeled them on the side over here. To go from xh to oh is 3. And the next step is to just sort of generalize what we did for the network, going from this node to these 4 nodes, right? That's what we got to do next, is the same idea. So if you just took the weights and you multiplied them on each node. So if you came here to 1 and you went, okay, W01, and this one is W11 times OH1, and then W21 times OH2, and then had 4 of those bad boys, you would see that it would be exactly the same thing as what we did before. So what I'm trying to find now is the compilation of all these, and that's going to be our, we'll call it XF1. This one is, of all these, is XF2, XF3, and it's not a XF4. All right, so now how do we get those? It's the same idea as this guy, where XF is equal to WHF transpose times OH. All right, so where OH was a 2 by 1, WHF transpose, so remember what WHF was, and I'll take so WHF is a 2 by 4, the transpose of that would be a 4 by 2. So this will be a 4 by 2, and then these line up, which is good, and it leaves you with a 4 by 1, which is what we want, because that's how many nodes are in the final layer. So we got a 4 by 1 vector. So to go from OH to XF, which is a 4 by 1, we're going to do the calculation number 4 over there. And then the final one, calculation number 5, is simply what's coming out of the network. So this will be OF1 through 4. So what would that be? Is just simply the same thing that we did in the hidden layer. We just take XF and the sigmoid of it. So OF vector 4 by 1 is equal to the sigmoid of XF, the input vector. And then we're done. So then we have OF, and that's what we're going to use in order to calculate our error. 4 by 1, it is a vector, and we're done. So what I'd like for you to notice is so I wrote notation here for a reason. Each one of these vectors that's going into the nodes is called the input vector for that layer. So XI is going to be so the first letter represents if it's input or output. The second letter represents what layer that it's going in, and then the little 3 by 1 is just the number of, for this particular, this 3 node by 2 node by 4 node just represents the number of components in that vector. So this is not this should be another letter. So O and I, and there should be the same size. So this is XH, OH, XF, OF, and so on and so forth. All right. So notice the notation, notice what the forward propagation and what the calculations are. These are what we are going to do in R for us. But you might need to do this at some point. Okay, so the next part that we talk about is, now we've done forward propagation, now we're going to end up doing what's called back propagation of the error. So we're going to propagate the error backwards. In order to do that, we need to think about, anyway, what this what the so this final or this node here has an output. So it's OF, and we'll just let it be OF because there's only one node here, and it has a target. And most of the time you're not going to hit the target, so you're going to have some error. So we'll let error equal whatever the target was minus OF minus your output of the final layer. So this is the error. This is the total error in the final layer. In the final layer, error is easy. But what about the? We'll let this be a hidden layer, and let this be the final layer. And this one's coming in here. This one's coming in. So we'll let this W11. This is 1, 2, and this is 1. This will be W2, 1. If this one is 3 and this one is 1, then how much of this error, so I didn't give you the number, but how much of that error can be attributed to this node when I backwards propagate it? So I'm going backwards now. And all we do is just use a simple proportionality. So if this weight is 3 and the weight on node 2 is 1, then all we're saying is that 3 over 3 plus 1, then 3/4 of the error can be attributed to node 1. And if that's 3/4, then obviously 1 over 3 plus 1, then 1/4 of the error to node 2. And why is that? Because of the weights. And that's all we're going to do. We're just going to proportion out the weights, have this normalizing constant here at the bottom so that I get a solid 1, or I mean, if you added up the amount of proportions, I mean, later on we're going to get rid of the proportion, but just for right now, let's just understand that all we're doing is just trying to find the proportion of error that's coming from one piece to the next. All right, so with that in mind, let's go ahead and find a hidden layer error. Of this network. And we'll see back propagation. Because what I want to do is I want to make this as easy as possible for us. Because the computation in a neural net is rather high already. So we're going to get, this will be OF1, this will be OF2, and my error in this one will be EF1 will equal whatever my target was for that node minus OF1. The error in this node, so the error in the final network is easy, right? You just take the target, whatever the target was, and you subtract whatever the output. So the error here is pretty straightforward, and we'll summarize this here in a second. But what I'm concerned with is the error in the nodes in the hidden layer. So let's look at node 1, because it produces more than 1, right? Because there's two arcs that are coming out of node 1. And those 2 arcs are going to produce error in both final layers. Both nodes of the final layer. So the amount of error that's produced here, if we just go back and we say, well, W11 times 1, right? So we just do the same sort of proportionality that we did here with W11, and then the other one that's contributing to it is W21, right? So those are the 2 arcs that are coming into the final layer, and the final layer has that amount of error. So let's just proportion that sucker out. So it'll be W11 using the same idea that we did up in the previous one, W11 over W11 plus W21. And then I'm going to multiply that by the error, EF1, and that'll give me the amount that comes from node 1 of the hidden layer to the final layer node 1, right? And then plus, because it's got another arc coming out of it, W12 over W12 plus W22 times EF2. So now what we're saying is, let's look at this node down here and notice that this arc's coming in W12, but that's not the only arc coming into W2, I'm sorry, into node 2. This one all is as well. So if we use the same idea, the proportionality that we did before, well, then I got W12 over both of these added together. And that's where you get the denominator. So that's the total amount of error. So this is the total error coming from that arc, from that node. So total error from node 1, and hidden. Now let's look at node 2. And if we do the same process with node 2, we'll get W21 over the same denominator because it's a normalizing constant, 21EF1 plus W22 over W12 plus W22 times EF2. All right, so, and then we could label this as the total error that's coming from node 2. But what we want to do now is we want to get rid of these normalizing constants. And the reason why we want to get rid of the normalizing constants is going to make our lives a lot easier. And oh, by the way, we have learning rates that we're multiplying by these errors and these deltas. And so we're not finding exact numbers. So if we were trying to find the exact real value using one data point, then that would be different. Then maybe we wouldn't get rid of the normalizing constant. But the problem is we're just making incrementally better steps when we start training this thing, and we need a whole bunch of data in order to do it. So the idea here is let's lose the normalizing constant. So that we can make our calculations. So it makes our calculations much easier. All right, let's see how that does. So if I start off with EF, right? EF we said was pretty straightforward. In this case, I have T1 minus OF1, T2 minus OF2, very easy to find, and that's just equal to EF1 and EF2. Very easy. EH, on the other hand, the error in the, so again, I'm using the E to be the error and the second letter to be the layer that we're talking about. And so I can rewrite this. Let's do that because it's going to be again, it's going to be a vector with two components. So if we lose the normalizing constant, we get W11 EF1 plus W, is that 12? Let me go up just a little bit. Yeah, W12 times EF2, W21 EF1 So what's another way to write that? W11, W12, W21, W22 times the vector EF1 and EF2. What's another way of writing that? This would be WHF. So this would be WHF, the vector WH, I'm sorry, the matrix WHF times the vector EF. Or here, let me use the capital E because that's what I used before. So now we notice that, okay, this one's easy to get, so I'm just doing subtraction, and this one's also easy to get. This one's also easy to get because I'm just doing a matrix times a vector, the vector that we just calculated. So that's all I got for today. What we're going to talk about next time is how we're going to use this error in order to update our weights. So be ready for that. And